Hello students, we have already learned the control chart X. Now we are going to learn the control chart R or the R charts. These are the control charts. Like the X bar charts, they are also meant for process variability. R charts are control charts for process variability. So both the X bar chart and the R chart are dealing with process variability. So the X bar chart defines the upper control limit and the lower control limit on the amount of variability we are willing to tolerate in the sample means. So we have studied X bar chart defines UCL and LCL on the amount of variability we are willing to tolerate in the sample means. So how much variability we can tolerate in the sample means, we are going to define it with the help of this X bar chart, which will give us the upper control limit and lower control limit. Then, but the sample means have moderating effect on the variability and they are less variable than individual observations. So X bar chart cannot be applied for individual observations. They are less variable when we compare it for the individual observations. So sample means, so X bar chart is dealing with the sample means. So they have the moderating effect on the variability and they are less variable when you check with that of the individual observations. So quality concerns are addressed to individual observations like the drive shaft diameter. So simple observations, individual observations like diameter of the drive shaft or the dimension of a particular component, those all will matter the quality of the product or the component. So in order to monitor the variability of individual observations, we are using another control chart and that chart is the R chart. So the X bar chart deals with the means of the sample. If you want to monitor the variability of individual observation, not the sum divided by the number of observation, but if you want to know the variability of individual observation, then we should use the control charts which are known as the R charts. So in this R charts, we plot the values of sample ranges for each of the sample. So here we are using the range, not the mean. So in R chart, we plot the values of sample ranges for each of the sample. The center line is placed at R bar and the control limits are calculated from the sampling distribution. So here in the X bar chart we have seen that the center line is the mean, but here it will be R bar, that is the range, is placed at R bar, and the control limits are calculated from the sampling distribution. Standard deviation of the sampling distribution can be written as, so R is sigma R, that is the standard deviation for the sampling distribution. R can be written as D3 into sigma, where sigma is the population standard deviation and D3 is a factor depending on the number of samples. So, where sigma is the standard deviation of the population. So, here we are going for individual observation. So, standard deviation for the population, that is the whole lot, is denoted by sigma, and D3 is the factor which depends on n, which is the sample size. So the control limits for R charts are given below. The upper control limit is given by R bar plus 3D3 R bar divided by D2, and lower control limit is R bar minus 3D3 R bar divided by D2. So D2 is also another factor which is depending on the value or sample size. So range is only convenient substitute for variability of the process. So range, that is the R chart, is a convenient substitute for variability of the process. It is simple to calculate, plot and understand when compared to the standard deviation. Range is simple to calculate, plot and understand compared to standard deviation. But range only considers the highest and lowest value in the distribution, and it will ignore all the other observations in the data set. Range considers highest and lowest values in a distribution and ignores all other observations in the data set. So, because it is ignoring all the other observations, it may also ignore the nature of variation among all the other observations and is mainly influenced only by the extreme values. So, as it is considering only two values, it is ignoring all the other values. The nature of variation among the observations is also ignored and is mainly influenced by the extreme values. So this range is measuring only two values. So the range can change significantly from one sample to the next sample in a given population. So range is measuring only two values. So it may change significantly from one sample to other sample in a given population. So now after we have studied the X bar chart and the R chart, we have to know the relative precision index. So what is the relative precision index? So the control limits for both the X bar chart and R chart, they do not consider the relationship between the work tolerance and process variability. The control limits for both X bar chart and R chart do not consider the relationship between tolerance and process variability. So as they are not showing any relationship between tolerance and process variability, these two charts do not provide any clue for the drifting of the process towards one side. So if the process is drifting towards one side, these charts, that is the X bar and R chart, they are not providing any clue about the drifting of the process. So to determine whether the process may be allowed to drift before the corrective action is taken, the relative precision index, that is RPI, is used. So to determine, so should we allow the process to drift or not? To know whether we should allow the process to drift or not, we are using this relative precision index. The relative precision index, which is also called as RPI, is used. So this will relate the process variability and the tolerance. This RPI relates the process variability to work tolerance. So RPI can be written as work tolerance divided by R bar. So after calculating this relative precision index, we can refer to a table to see whether for a given sample size the process is low, medium or high relative precision. If low, the process is unsatisfactory and likely to produce defective parts. If the RPI, that is relative precision index, is low, then the process is unsatisfactory and is likely to produce defective parts. If the RPI is medium, then the process is satisfactory but needs frequent review to ensure that it is under control. But needs frequent review. High, then a drift can be allowed to take place before the setting is adjusted. So if RPI is high, then a drift can be allowed. So we can allow the process to drift towards any control limit before the setting is adjusted. So here the table for a sample size of 2, the RPI with low relative precision is less than 6. So unsatisfactory and rejection of the part is imminent. That is, we cannot avoid the rejection of the parts. So we have to reject the parts. If the sample size is 3 and you see that the relative precision index is low, then also we will reject it. Here the relative precision index is medium up to 6 to 7, then it is satisfactory if the averages are within control limit. Similarly, for different sample sizes, we see that the relative precision index is being compared here, and here we see that if the relative precision index is high, then it is satisfactory if the averages are within modified limits. So this is all about the R chart and also the relative precision index, which is giving us the relationship between the work tolerance and the process variability. I hope you have understood the topic. Thank you.